Most AI tutorials show you one tool at a time. You get a quick demo of an LM here, a vector database there, maybe a workflow tool in another video. Each one looks impressive on its own, but it's hard to see how they fit together into one working system. If you're anything like me, you've probably watched a lot of these videos, bookmarked a bunch of GitHub repos, and still felt unsure how to glue everything into a real day setup. The missing piece is a clear end-to-end map. In this video, I'll walk you through my own AI knowledge lab, a 24-container stack running on a single machine at home. You'll see the big picture architecture, the main layers, and how the pieces talk to each other. The goal is simple: give you a mental model you can adapt. So instead of 20 disconnected tools, you have one coherent AI lab that actually supports your work. Let's start with the kind of engineer this video is for. Imagine Ken. He's a senior software engineer who has tried a lot of tools. He runs local LLMs with Ollama. He uses Qdrant as a vector database. He has Nathan for workflows, maybe Neo4 for relationships, and Prometheus and Grafana to keep an eye on things. Each tool came from a different blog post, a different tutorial, or a different weekend experiment. He followed the steps, spun up the containers, and got everything running. On paper, he now has a serious stack. But when he looks at his Docker list, what he sees is a pile of parts, not a complete machine. He has 20+ containers, and still no clear mental model of how data should flow, or which piece is responsible for what. This AI Knowledge Lab is my attempt to solve that problem. It turns many individual tools into one coherent system, so someone like Ken can finally say, "Okay, now I see how this all fits together." Now let's zoom out and look at the high-level map of my AI Knowledge Lab. Everything runs in Docker containers on a single physical machine. Most services share one Docker network, and each important service stores its data on a persistent volume on the host. So even if a container restarts or gets updated, the data stays. To keep the mental model simple, I grouped the 24 containers into a set of layers. The model layer is where local LLMs live. The knowledge layer handles para-style knowledge and semantic search. The data and graph layer manages structured data and relationships. The workflow layer runs automation. The monitoring layer gives observability. And the frontends are where humans actually interact with the system. Around these core layers are a few supporting services, things like search, developer tools, and media services that make the lab more useful in daily life, but don't change the core architecture. In the rest of this video, we'll walk through each layer at a high level. As you watch, try to imagine where your existing tools would sit, and where you might want to plug in new capabilities. First, let's look at the model layer. This is the foundation, because it's where the local language models actually live. In this lab, that role is handled by Ollama. Ollama runs models like Llama 3.1, and also an embedding model that other services can call. It exposes simple HTTP endpoints for text generation and for embeddings. That means anything on the Docker network can treat the models like a standard web service. By isolating models in their own layer, the rest of the system doesn't need to care which exact model is running. If a better LM appears, or if I wanted to experiment with a different embedding model, I can change things inside this layer without rewriting the knowledge layer, the workflows, or the frontends. So the key idea here is, models are just one layer with clear boundaries. They're powerful, but they're also swappable parts inside a bigger machine. Next is the knowledge layer, which acts like the brain of the lab. Here, a service called Llama exposes APIs for managing projects, areas, resources, and archives using a para-style structure. In practice, that means I can organize notes, documents, and references in a way that mirrors how I actually work, instead of one giant, messy bucket. When new content arrives, things like notes, PDFs or transcripts, the Llama service handles chunking those documents into smaller pieces and then calls the embedding model in the model layer. The resulting embeddings, together with metadata, are stored in Qdrant, the vector database. Qdrant is what makes semantic search possible. It lets the system find relevant chunks of information, even when the exact words don't match the query. Combined with the parastructure in the Llama service, this layer turns raw documents into something much closer to navigable knowledge. So if the model layer is the engine, the knowledge layer is the organized memory that the rest of the lab can query and build on. Underneath the knowledge layer sits the data and graph layer. Postgres is the workhorse for structured, relational data. It stores tables for resources, indices, and other application state that needs strong consistency and traditional querying. When something in the lab needs a well-defined schema and reliable transactions, it usually goes into Postgres. Neo4j lives alongside Postgres, but focuses on relationships. It shines when the important thing is not just the items themselves, but how they connect. For example, mapping which concepts appear across which documents, or how different people, projects, and topics are related. By keeping these responsibilities separate from the vector database in the knowledge layer, the lab gets 3 different ways to think about data: semantic similarity through embeddings, structured queries through SQL, and relationship-focused queries through graphs. Together, they cover a wide range of questions the system might need to answer. Above the core data layers is the workflow layer, powered by Natin. This is where the automation lives. Natin lets me build flows visually, as a series of connected nodes. A typical flow might watch a folder for a new PDF, or listen for a new YouTube transcript. When something arrives, the workflow calls the Llama service to chunk the content, sends the text to the embedding model, and then updates Qdrant and Postgres with the new data. Because these workflows are visible as graphs instead of hidden in scripts, they are much easier to tweak, debug, and share. If I want to change where content comes from or how it's processed, I usually only need to adjust a node or two in Natin. The big idea is that the workflow layer keeps the lab evolving. As new sources or tasks appear, they get wired in here, rather than buried in hard-coded scripts scattered across the system. To keep this lab stable, monitoring is treated as a first-class layer, not an afterthought. Prometheus is the time series database that scrapes metrics from the machine and from the containers. Exporters like Node exporter expose CPU, memory, disk, and other host-level stats. DCGM adds GPU metrics so I can see how the models are actually using the hardware. Grafana sits on top and turns all of those raw numbers into dashboards. At a glance, I can see CPU and GPU usage, memory pressure, disk space, and whether key services are up or down. When something misbehaves, I usually notice it in Grafana before I feel it in my day-to-day work. This layer doesn't do any AI itself, but it makes the whole lab safer to experiment with. When you can see what's happening, you're much more willing to push the system and learn from it. Finally, there is the front-end layer, where humans actually touch the system. WordPress powers a site where I can publish or test content that connects back to the knowledge layer. It's a familiar interface that can pull in insights, summaries, or structured data from the rest of the stack. OpenWebUI sits directly in front of the models. It gives me an interactive chat interface where I can run prompts, test new models, and experiment with retrieval setups that talk to Qdrant or Postgres behind the scenes. Nginx acts as the traffic cop for all of this. It routes external requests to the right front end, handles basic routing and security, and keeps URLs clean. Together, these front ends turn a bunch of back-end services into something that feels like a usable product, not just a lab on a terminal screen. Now, let's talk about the glue that makes all these containers feel like one system instead of 20 G4 islands. First is the network. Most services share a Docker network called Qdrant. On that network, each service can talk to others by name. So instead of hard-coding IP addresses, a workflow can just call HTTP Ollama or HTTP Qdrant or HTTP Postgres. This makes the system much easier to configure, move, or extend. Second is storage. Data lives on host volumes that are mounted into the containers. Postgres, Qdrant, Neo4j, and other key services all write their databases and logs into directories on the machine. If a container crashes, gets rebuilt, or updates to a new version, those volumes stay in place. This combination, a shared internal network plus persistent volumes, means the stack behaves like one cohesive AI lab, not a set of temporary demos. Services can find each other reliably, and your knowledge survives beyond any single container's life. This is not the only way to build an AI platform, but it's a pattern that matches the goals of an engineer who wants control and understanding. One principle is local control. Models and data run on a self-hosted machine, so nothing leaves the home lab unless it is meant to. That matters for privacy, cost, and the freedom to experiment without hitting external limits. Another principle is modular layers. Each major function, models, knowledge, data, workflows, monitoring, and frontends, sits in its own layer. When something changes, you aim to update one layer at a time, instead of pulling on a knot of cross-dependencies. Observability, by default, is the third principle. If you can't see what the system is doing, you can't safely evolve it. Monitoring is built in from the start, not bolted on at the end. The trade-off is obvious. This setup is more complex than using one managed cloud service with a single AA button. But in exchange, you gain a deep, practical understanding of how the parts fit together, and a lab you can extend in many directions over time. Let's recap what you've just seen. This AI Knowledge Lab is a 24-container stack running on a single machine. It is organized into clear layers: models, knowledge, data and graph, workflows, monitoring, and frontends. All of these are tied together by a shared Docker network and persistent storage on the host. The model layer runs local LLMs. The knowledge layer turns documents into searchable knowledge. The data and graph layer handles structured information and relationships. The workflow layer automates how new content moves through the system. The monitoring layer keeps everything observable. And the frontends are where you and other people actually use the lab. In this explainer, you've seen the big picture map. In the next videos, we'll zoom into specific parts of the lab, starting with how the knowledge layer turns your documents into iCircable knowledge, and then how monitoring keeps everything healthy over time. If this architecture gives you ideas for your own lab, feel free to adapt it. Swap in your favorite tools, scale it up or down, and make it your own. And if you end up building a version of this, it would be great to see what you add or change.